Hi everybody, welcome back to Chem 140. I forgot that yesterday we had talked about that I was going to do Unit 10 because Unit 10 is short, so you probably got 2 announcements from me saying, hey, it's a Q&A, and then nobody shows up. And then there was a second announcement that said, hey, I'm an idiot, we're actually lecturing. So we're going to do a short lecture on Unit 10 because it's only like 16 slides long. Probably won't take more than the first hour. And then I'll open it up for questions for the Q&A. And then we'll just do whatever it is that we do on Wednesdays. I don't know. For me, that is getting ready to teach the next class. For you, hopefully it's working on your lab or whatever. Speaking of your lab worksheet will be due on Thursday for lab number 3. We'll talk about lab number 4 next week when we get there. All right, so let's talk about bonding. We've already talked about ionic bonding. Ionic bonding was the attraction of... Oh, is the class title 131? Oh, boo. That could be why there aren't that many people. Okay. Let me fix that real quick. Yeah, I forgot to change it. And then this is just going to say Unit 10. I sometimes do that, sorry. Okay, if you hit refresh, it should say the correct... it'll say the correct title. Sorry about that. Thanks for bringing that to my attention, though, because I'm sure that confuses people, and then they're like, wait, I don't want to be in this one. That's for some other class. Oh, yeah, now the number of people that are coming in is, like, double. Okay. Yeah, I noticed there were, like, 2 people right before class. I was like, that's weird. Maybe nobody wants to come to this lecture because they think it's a Q&A. So, I've sort of messed up everything. Yeah. If you aren't sure what it is, just click on it in the future, and then also let me know that I have titled it incorrectly, because I can fix that. Alright, we've already talked about ionic bonding, where you have opposite charges that are attracted to each other. Now we're going to talk about covalent bonding. Covalent bonding has to be different somehow, because compounds with covalent properties are very different. For example, if I look at water or gasoline, these are substances that are liquids at room temperature. Almost all ionic compounds are solid at room temperature, and are solid until you heat them up to like 800 degrees or something ridiculous. But water and gasoline aren't. They're liquid at room temperature. What about stuff in the air like oxygen and nitrogen? Those are gases at room temperature. And those are atoms that are bonded together, so what's the deal there? Also, if we were to like grind up the solids that we have available, like wax doesn't like chip into chunks like salt does. If you have a giant salt crystal, you can cleave off like chunks of it that make very flat surfaces. But for something like wax, like you can't cleave that by just like you would need to take a knife to it to do that. Wax is very soft, like it would just break into like long stringy pieces, really. Or if you took something like sugar and you tried to cleave it cleanly, you'd find that you would just end up making a mess. You'd end up getting powdered sugar. So there must be something about these that is different. What is it that is different about these compounds versus ionic compounds? And it has to do with their bonding. Now, the difference in bonding arises from the fact that the elements that are involved here don't have electrons to pass around. So, for example, we're going to look at fluorine here. And I'm going to draw a picture of it. Oops, I'm going into the wrong screen to do that. So if I was going to draw the Lewis dot structure of fluorine, each fluorine would have 7 valence electrons. Oh, I need to drink more water. Hold on. Now, let's suppose that I wanted to get everything to satisfy the octet rule, and the only thing that I can really do is I could just pass this electron over here. This would have 8 electrons and have a negative charge, but this would only have 6 electrons and be positive. This one would not be at an octet, but this one would. And it turns out that no way I pass electrons back and forth is ever going to get both of these at the same time to be an octet. So electron transfer must not occur for these compounds because I can't get to the octet that way. So instead, what happens is that these atoms share their valence electrons. And so if atoms share covalent electrons with each other, or I'm sorry, if they share valence electrons with each other, they become covalent. The co means communal. Now, how exactly does this work? If I take my 2 fluorine atoms and I try and shuffle electrons between them, I will never get an octet. But what if I do this? And I just sort of set them next to each other. Then what happens if I do this? So I'm going to circle a fluorine atom and watch what I do. Here's one fluorine atom. Does the fluorine atom circled in red have an octet? Yeah, I've circled 8 electrons. That looks good. How about the one I'm circling in blue? Ooh. It has an octet too. If we can have this be our octet, then the atoms will be perfectly stable and the molecule will form. Now you might notice that in the middle here I have my shared electrons. And yes, we double counted them. We did that because that was how we made this work. We're double counting them, and we're basically cheating, but that's fine. Atoms don't know that. They're stupid. They don't have brains. So by making these atoms share electrons with each other, we can create a stable octet for everything. And so this is what a covalent bond looks like. So our goal is going to be to take our electrons from atoms and make shared opportunities. Now, the way that this works, and this is going to come up on a later slide, is that when I draw my valence electrons around the atom here, I'm going to end up with some number of unpaired electrons. Unpaired electrons can be shared. What about the paired electrons, though? Well, they just hang out. Paired electrons don't do anything. Mostly because if I was going to make a bond with paired electrons, I'd have to give both of them away. And if I did that, that wouldn't be sharing. Now, in advanced classes, in like 161, we talk very, very briefly about this, but mostly in 361, in the third year chemistry. You can actually make covalent bonds with paired electrons, but for our purposes in this class, we're only ever going to make bonds using unpaired electrons. So the paired electrons, they're going to sit there. And if you take an unpaired electron from each atom, you can then make a paired electron right here. So here's our paired electron that we made. And because it's between two atoms, it's our bond. All right. So this is our covalent bond. Now, a covalent bond forms for any pair of electrons that is shared. I'm not sure why there's an underscore here. That's okay. Now, we're going to learn that you can share multiple pairs if you want to between atoms. If you have multiple single electrons, you could use them to make multiple bonds between two atoms. But for now, we're just going to represent our pair of electrons that is between two atoms as a single bond. And we're going to work with that, just that for now. Now, instead of drawing dots between two atoms, the convention is to draw a line. On the sides here, we have the non-bonding pairs. Remember that the paired electrons just hang out. They don't do anything. The single electrons will pair up with other single electrons from other atoms. Now, when you share your electrons to make your bonds, there's a few important things that you want to note as your goal to make these structures. So the first thing is that every time you draw a line and you're counting all of your electrons around your molecule, the line counts as 2, but it counts as 2 for each atom it connects. So if I go back here and I'm like, okay, let's check to see that I satisfy the octet rule. So a common strategy would be to just circle an atom. If you pass through a line, the line counts as 2 electrons. Each of these is 1 electron. So if I was counting these, I'd go 1, 2, 3, 4, 5, 6, and the line is 8. Then I'd do the same thing for the one on the other side over here. 1, 2, 3, 4, 5, 6, and then the bond is 8. So everything has satisfied the octet rule. So when you're counting the octet rule for your molecules, just as a check at the end to see if you have done it correctly, make sure that you count the bond as 2 for both sides, because they're shared. Remember that. Now, there is an exception to this. Not everything wants 8 electrons. The exception is hydrogen. Hydrogen only wants 2 electrons. And the reason for this is because hydrogen is small. Hydrogen is a single proton and a single electron, and all it can really do is take 1 additional electron. It doesn't have any electrons that are paired that are already around it. Hydrogen follows what's called the duet rule. If you ever have a Lewis structure where you're trying to put hydrogen in there, all you need to do is connect it to something that has 1 unpaired electron with its hydrogen's 1 unpaired electron. Now, in some cases, you need to share more than 1 electron. Let's look at oxygen real quick and see how that would work. In this case right here, I have 2 unpaired electrons on each atom. Now, if I could pair them like, oops, that's not the right pen, sorry. If I could pair them like, say, this, so pair this guy over here, and then pair this one over here, I could make 2 pairs of 2. So if I do that, this is what I would get. Everything is an octet because those 4 electrons in the middle are shared. And since 2 electrons makes a line for a bond, we'll just write 2 lines. This is called a double bond. A double bond has 2 pairs of electrons in there. That's not at all what I wanted that to do. I clicked on the wrong pen. That's what went on there. Can't even see that. There we go. So if I'm checking the octet here, same rules apply. So, oops, I don't want to use yellow as my marker. It's impossible to see. So I circle this. 1, 2, 3, 4. Align this 2 and align this 2. So that's 8 electrons around my oxygen. So I've satisfied the octet rule. Now, how many bonds are possible? You can actually get up to 3. You can do a triple bond with some molecules, such as carbon or nitrogen. 4 is not possible, if only because of geometry. So for like carbon, you can't make all 4 electrons bond in one direction. So what I want you to try and do is I want you to try and draw the Lewis structure for nitrogen. So draw out all the valence electrons on a nitrogen atom, put another nitrogen atom next to it, and then connect all of the unpaired electrons together so that everything has an octet. And tell me what you get. How many bonds should nitrogen have? N2. We'll go over the answer in just a second. All right, have you drawn the Lewis structure for N2? What you think it is, yeah, anyway. One more, oops, I'm accidentally clicked on mute there. One more minute, we'll go over the answers. All right, so let's draw the Lewis structure here. So for nitrogen, nitrogen should have 5 unpaired electrons. We'll draw another nitrogen with 5 unpaired electrons. And then I'm going to just pair up the unpaired electrons. So these 3 sets of 2 are going to come into the middle here as my bonds. So here's my nitrogen. I got 1, 2, 3 sets of 2. And then I draw the non-bonding electrons on the sides. You do have to draw the non-bonding electrons because otherwise when you go and check your electrons for octets to make sure everything has an octet, they won't be there, and then you won't get an octet and you'll think you did it wrong. So now we can check. We'll circle. 1, 2, 3, 4, 5, 6, 7, 8. Each bond counts as 2. 1, 2, 3, 4, 5, 6, 7, 8. Each bond counts as 2. So we've got an octet for everything in this molecule, so this is the correct structure. And it should appear on the screen. No, it doesn't appear on the screen, but that's okay. Now, is there a systematic way to figure out the number of bonds that each atom forms? And the answer is kind of. Typically speaking, at least for this class, before we get to let's break all the rules in 161, the molecules that we're going to be working with will make a number of bonds that is equal to the number of unpaired electrons they have. So what that means is that anything in group 7, any element in group 7, such as say bromine only has 1 unpaired electron because it starts with 7. So it's only going to make 1 bond. It will never make 2. For an element in group 6A like sulfur, I can make 2 bonds to things because I have 2 unpaired electrons. But I could also instead just make 2 bonds to the same thing. What's important is that I have the potential to make 2 bonds. Whether it's to the same thing or different things, it doesn't matter. For group 5A atoms like nitrogen, I can make 3 bonds. And for group 4A atoms, I can make 4 bonds. If I go further to the left than that, I end up with most of the stuff being metals. And metals don't form covalent bonds. They form ionic bonds instead. The exception would be boron, and boron being if boron only has 3 electrons, it'll make 3 bonds. Boron, though, is kind of weird. We'll talk more about boron in 161. There is a little formula that you can use to figure out the number of bonds something makes, and that is whatever 8 minus the group number comes to whenever you are looking at the groups with the A designation. Otherwise, use the ones digit. So if you're in element in group 16, take the ones digit out of that. 8 minus 6 is 2. That's how many bonds that tends to make. Now, notice that I'm saying tens, because in 161, when we get to expanded octets and elements that break all these rules, there will be exceptions. But for the elements that we're going to look at in this class, these ground rules will work just fine. All right, so now using all these guidelines that I've talked about, what I want you to do is try and draw Lewis structures of these molecules. So we got Cl2, draw all of the dots around each Cl, and then try and figure out how the bonds connect together. Then do that for BRF, CF4, H2O, OF2, and C2H4. Only one of these molecules, only this one down here, is going to require you to make more than 1 bond between 2 atoms. Okay. All the rest of them just have single bonds, but I want you to just try and practice this to get in the habit of it. So draw these molecules. We'll go over the answers very shortly. One more minute to go. We'll go over the answers after that. All right, let's go over the answers here. We'll go over to this slide. That didn't work. There we go. Ah, there we go. Oh, Photoshop. Why? Why do you? There we go. Okay. So let's do Cl2. So I'm going to draw my chlorine. So 1, 2, 3, 4, 5, 6, 7. Chlorine, 1, 2, 3, 4, 5, 6, 7. We should all know how many valence electrons each of these has by now. And I can connect these two together so that my chlorine looks like this. There we go. Now, interestingly enough, chlorine and bromine have the exact same Lewis structure. They have the same number of dots. And chlorine and fluorine also have the same number of valence electrons. So, if I make this molecule, it's going to look exactly the same with the same number of dots. The identity of atoms does not matter. It's the number of valence electrons around the outsides that dictate bonding. Okay, let's do CF4. So I got carbon, and carbon only has 4 valence electrons like that. And then I have 4 fluorines, and each fluorine's going to have 7 valence electrons. I'm going to just arrange them like this, in such a way that my single electron here just points inward. And we'll just make these sharing pairs. And then, yes, you got to fill in the dots after. There you go. That's CF4. We got H2O. So oxygen has 6 valence electrons. Hydrogen only has 1 valence electron, but that's fine because it only needs 2. So we're just going to share these 2 and these 2. There you go. There's water. Now for OF2, I end up in the same situation. Let's just erase this here. There's my oxygen. Fluorine looks like this with 7 valence electrons. I did that incorrectly, but that's okay. And so for OF2, we would get a molecule that looks like this. There you go. Notice how it looks just like water. And that's intended, because there's 1 unpaired electron on both hydrogen and fluorine, so they're going to bond very similarly. Finally, we have C2H4, which we'll do down here. So each carbon has 4 electrons. I got 4 hydrogens here. How the heck do I make this work? Why doesn't hydrogen have any electrons around it? Because it only has 1 to start with. And when it pairs, it makes 2. Remember that hydrogen follows the duet rule. So you don't put any extra electrons around hydrogen because it didn't start with any. It starts with 1 valence electron, and it ends with 2 when you make a bond. What do I do here? Well, if I bond these 2, I could connect these together. Then I have all these H's. So let's just start putting H's in places and see what we get. Where do I put these other 2? Well, if I put them on the same side, let's suppose that I do this one right here. And then I decided, oh, I want to do this one right here. Here's what I would get for my result. So I'd have C, H bonding, H bonding, H bonding right here. A bond like that. And I have these unpaired electrons here. Did I satisfy the octet rule for everything? The answer is no. No, I didn't. If I check the octet rule right here, I have 8, because 2, 4, 6, 8, that's fine. But here, I only have 2, 4, 5, 6. So this structure is wrong. I need to satisfy the octet rule for everything. So, if you get a structure that's wrong, you gotta start over. You gotta try again. We'll just do that. So here's my carbon again. Here's my carbon again. I mean, I definitely want to connect these 2 together. Now what do I do? Okay, well, maybe I could just pair these and these like that. And now I have leftover electrons, 1 on each atom. Well, now I can just bond these 2 together, right? So when I make my structure, I get C with a double bond between it. And then each carbon has 2 hydrogens on its own. Now when I go check octets, like this, 2, 4, 6, 8, that works. 2, 4, 6, 8, that works too. So this is the correct structure for C2H4. Remember that our goal is to follow the octet rule every single time, with the exception of hydrogen. Hydrogen only needs 2 electrons. It just follows its own rule. Oops, that's the wrong thing. There we go. All right. Now, for that last molecule that we did over here, if I go back here, you can see that, like, there starts to get to a point where trying to figure out how to make these atoms bond with each other becomes difficult. Like, you can guess what the bonding might be, and eventually you will get there. So, like, C2H4 is not terribly difficult. But what if I gave you C6H6 and I said, okay, take all of these pieces and bond them together? So we'll just go over here and do that. And so I say, oops, that didn't work. There we go. And I give you these atoms and I say, okay, bond everything such that all of the electrons are connected and everything has an octet. And it would take a lot of tries for you to get to the correct structure. Like, that would be a miserable joke to do, right? So as molecules get more complicated, this strategy of, oh, just pair together the unpaired electrons doesn't really work anymore. It's what's actually happening, but as far as, like, solving the structure is concerned, that's very difficult. So we need an easier way to draw Lewis structures, and the easier way that we're going to propose is this plan right here. This is called the 5-step plan for Lewis structures. And so when you construct a Lewis structure for a molecule, you're always going to follow these 5 rules in order. If you go out of order, you get the wrong structure, and that's important. Don't mix up the order of these rules. All right, so the first rule of Lewis structures is don't talk about Lewis structures. No, I'm just kidding. Fight Club is an old movie. I don't know how long I can keep making that joke. The first rule of making a Lewis structure for a larger molecule is to count all of the electrons that are available for bonding in the molecule. Since each atom brings its own number of valence electrons, like, for example, if I was going to make C2H2, for example, the total number of electrons that I could use would just be the number of dots that I was writing. So I'd go, okay, each carbon is worth 4, and each hydrogen is worth 1. So if my formula was C2H2, I would say, okay, I have 2 carbons and each one gives me 4 electrons. I have 2 hydrogens and each one gives me 1 electron. So my structure should have 10 electrons distributed through it somehow. That'll be true for whatever structure you draw. Count all the electrons by just looking at each atom and counting the number of valence electrons it has from the periodic table, and just tally them up. Once you have a tally, you're going to make a framework. Your framework is just a rough sketch with all of the initial bonds in your structure drawn. So you're going to write all your single bonds in, how you think the molecule is constructed. Now, when I give you a formula, the formula is written to give you a hint about how it's constructed. The first atom that is written is going to be the central atom in your structure. The only exception is H. H can never be the first or the central atom. It can be first if it's an acid, but that's a special definition. If H is listed first, the second element is the central atom. So if I give you CO2, draw C with a bunch of O's surrounding it. If I give you NO3, draw N in the middle and then the O's around it. If I give you H2O, H can't be the central atom. The second atom must be the central atom. So draw O with H's around it. Now, for our C2H4 example, if you have multiple of the central atom, try and just keep them in the center as much as you can and distribute everything around it symmetrically, if possible. Generally speaking, the molecules we're going to be working with will have some degree of symmetry, and not like 3 on one side and 1 on the other. All right. Once you have counted all your electrons and drawn this framework in there, you have to account for the electrons that you are using from your total. So if you draw your framework and you make a bond, each bond deducts 2 electrons from the total number of electrons available. You can't over budget electrons. If you only have 10 to work with, you have to make a structure that uses all 10 and no more. Likewise, you can't destroy electrons. If you have extra electrons left over, your structure is incorrect. Make sure that you are using all the electrons that are given to you. All right. Once you have your framework down, you're going to have extra electrons left over that you're going to need to put somewhere. The first place that you put electrons around are the outer atoms. So complete the octets. And the wording here is kind of dumb. Put electrons around atoms bonded to the central atom. We'll just call these outer atoms. So you're going to take all your electrons and just dump them on the atoms on the outside until they have octets. And then if you have extra leftover electrons, you're going to complete the octet on the central atom. Finally, when you are done with all your electrons, because this should use up all your electrons, anything left over goes on the central atom. If you don't have enough electrons for the central atom, then you start making multiple bonds by using the outer electron pairs. So this kind of goes against what we were saying before, where the lone pairs that we would draw don't do anything. But in this scheme, what we are doing is a model. Okay, we're not actually doing what the bonding would do. We're just doing a shortcut to get to the correct structure. So if you run out of electrons for the central atom and you can't give it an octet, you can always share any pair of electrons from an outer atom. And you're going to see that in a second because we're going to do CO2, where you have to do this. Now, if at any point you are drawing your structure and you notice, oh, everything has an octet, or all my hydrogens have 2, stop. That is enough. You have the correct structure. So you could be done with the structure as early as step 2. But go through all the steps one at a time from 1 to 5. Don't skip any steps. Don't do them out of order. Don't go back. If you do the steps out of order, you'll get the wrong result. So be careful. So let's do CO2. Let's follow this idea for CO2. Where is my... There it is. All right, we're going to use the 5-step approach. There we go. Okay. So step 1 of the 5-step plan is to count valence electrons. So I'm working with CO2. Excuse me. If I look on the periodic table, carbon is worth 4 valence electrons because it's in group 4A or 14. Each oxygen contributes 6 valence electrons because each of the oxygen atom is found in group 6A or group 16. So how many electrons do I have to work with? 6 times 2 is 12, plus 4 is 16. So my Lewis structure should have 16 electrons. And if you want to check it, you could draw the Lewis structure for CO2 as individual atoms here. Oops, I didn't mean to do that. And count how many dots there are. 1, 2, 3, 4, 6, 8, 9, 10, 12, 14, 15, 16. And you'd see you get the same amount. All right, step 2 is to draw our framework. You think of this as like a skeleton for our molecule. So what atom should go in the center? It should be the atom that's listed first. So I'm going to put C in the middle. I'm going to put O's on the outsides. And this isn't a framework because I haven't connected them together. So I'm going to connect these together. So here's my first bond and here's my second bond. Each bond is 2 electrons. So I have to deduct 2 electrons per bond from my total. All right, actually, let's just do this. For step 3, we want to put electrons around the outer octet. So let me copy my structure here. This is what we've got so far. Now we're going to put our remaining electrons around the outer atoms until everything has an octet. And if we have any leftover electrons, we'll just stop and throw them on the center later. If we run out of electrons, we just stop where we get to. The way that you want to do this is you want to satisfy the octet of each atom one at a time. So that's going to be my hint here. Do each separately. So I'm going to start with this left oxygen over here, and this is what I'm going to do. Dot, 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 dot. I'm going to stop there because if I count the octet, I have 6 of these by themselves here, and then a bond which counts for 2. So that atom is good. I wrote 6 dots down, though, so I got to deduct it from my total. Now I'm going to do the other thing to the other side. Or the same thing to the other side, sorry. 1, 2, 3, 4, 5, 6. Notice that I'm putting them in pairs instead of doing 1 dot at a time. Because, again, this is a model, and it's just faster to do it that way. And any electrons... Oh, excuse me, I'm getting yawn. Any electrons that are not bonding will be paired, because they are non-bonding pairs. So we might as well just draw them as pairs right now. So I have my octet there. 1, 2, 3, 4, 5, 6. And then the bond counts as 2 for 8. But I've used all my electrons. So when I get to step 4, which is to put remaining electrons on the internet or the inner octet, I just sort of get like the shrug emote, right? I don't have any. I have no more electrons. So what do I do with that? Well, I have to skip the step. There's nothing I can do to my structure. So the last thing that we can do is make multiple bonds. So I'm going to copy our structure from before. There we go. And I need to make multiple bonds by donating pairs of electrons toward the central atom. So what I'm going to do is I'm going to take this pair of electrons here. I'm going to put it in here to make a double bond. And if I do that, my structure will now look like this. So here are the electrons that we didn't use. This side hasn't changed yet. And the 2 electrons that I circled up here are now here. If I check my octet up here, I have 8 because I have 6 individual, 3 pairs of 2, and then this bond right here. Down here, now I have 4 pairs of 2, but 2 bonds, so that's still an octet. If I check for carbon up here, I only have 4 electrons, but now it has 6. So you can see that we're going in the right direction. We are getting this closer to being an octet. I need to donate 2 more electrons, and remember what we said about symmetry, so we'll just take them from this side. And our structure will then look like this. So that's everything that didn't change, but here's the extra bond that I made from doing this donation. Okay, now that I made the structure, we gotta check for octets. We already checked this oxygen, it's fine. This oxygen on the other side is identical, so it's gotta be fine. But if we check this carbon in the middle, 2, 4, 6, 8, hey, that's fine too. So the structure that we have drawn is the correct Lewis structure. It looks like this. There you go. So that's how we draw the Lewis structure for CO2. The Lewis structure for CO2 required all 5 steps, so we had to go through them 1 through 5. Sometimes you have to do all the steps, sometimes you don't. Some steps you will get to and you will realize, oh, I cannot do them because either it's already been done or I lack the electrons to do it. In that case, go to the next step, but you can't go back. Go do the steps in order. All right, my slides walk you through that, but we've already done these. So that's great. All right, so for practice, what I want you to try and do is do the Lewis structure for this. This is ammonia, NH3. Count the number of electrons, draw the framework, distribute the electrons, make multiple bonds if you have to. Should be able to do this in about 2.5, 3 minutes, okay? So I'll see you in a bit. All right, one more minute, and we'll go over the answer. All right, let's go over the answer. So how many electrons does ammonia give you? So nitrogen is worth 5. It's in group 5A. Hydrogen's in group 1A, and there are 3 of them. So I should have 8 electrons to draw my structure. So let's draw the framework. Nitrogen is listed first. It goes in the middle. We'll just put the H's around it. I'm going to then connect them. So I made 3 connections. That's 6 electrons used. So I have 2 left. Now I got to do outer octets, but hydrogen doesn't follow the octet rule. It just wants 2 electrons. So each of these hydrogens is done. So I can go on to the next step. Put the remaining electrons on the central atom. Okay, we'll do that. Now there are no electrons left. Finally, make multiple bonds if necessary. Well, everything has an octet except for hydrogen, which only needs 2, and it's fine anyway. So the structure is complete. This is the correct structure. And you'll notice that mine on the screen here looks like the one that I just drew, although the angles are different. In this class, we aren't really going to care about the geometry of our molecules. If you do everything at right angles or you make triangles or whatever, it's totally fine. All right, where are we on? Oh, I went well over the break. So what we'll do is, so this is the last slide of the chapter. Like, we're all done here after this. I'm going to pause for now. We're going to take our 10-minute break, but what I want you to do is, if you have other questions that you would like asked after we do these examples for the Q&A part, put them in the chat during the break here, and we'll get to them afterwards. But if you don't have any questions, then after we do these slides, we'll just call it a day. Okay? So 10 minutes to think of some questions, type them in the chat, get them in there so that I know that I have content to go over afterwards. Okay? So start the timer. We'll go back over to, oops, that's the wrong window. Back over here and get more Donkey Kong Country 2 going. All right, we're back. Donkey Kong Country 2 has such a good soundtrack. All right, so there were some questions that were posted in the chat. We're going to get to those after we do these structures, but first I want to give you a chance to try and draw them. So I have sort of randomly assorted some molecules that need double bonds, triple bonds, all of them are single bonds, or whatever in here. But follow the same rules that we've been doing. Put the atom that's listed first in the middle, and then arrange the other ones around the outside. And then follow all the rules. So do all of these Lewis structures, and I'll give you about like 10 minutes or so to do them, because there's a lot of them. And once we get back, we'll do all the answers, and then I'll answer whatever lab questions that we have in the chat. Or if you have any other questions that you think of during that time, go ahead and keep doing that. So I'm going to shut myself up, and we'll see you in a bit. How are we doing? Do we need more time? Or are we ready to go over the answers? Let me know. Okay, so like 1 or 2 more minutes for other people then. More time. Okay, keep going. I realize there are a lot of these. All right. Let's go over the answers. We'll go over here. I guess I don't really need the top part there. There we go. just because I don't want this to take too long. All right, so I'm not going to write out each step explicitly like we've been doing for the sample problems. I'm going to instead, we're going to do all the steps, obviously, but I'm going to just do them a little bit faster, I guess we'll say. Okay, so we're going to count our valence electrons. Each carbon is worth 4. Each sulfur is worth 6, and there are 2 of them. So that gives me 16 to work with. And then carbon is my central atom, so I'm going to put the sulfurs on the other sides. So we'll make our framework. That's 2 plus 2 is 4, so I have 12 left. We'll put the remaining 12 around the outside. 6, 7, 8, 9, 10, 11, 12. And then we'll put the remaining 0 on the inside, so can't do that. I'm an octet here. So I'm going to erase a pair over here to make a double bond. I'm going to erase a pair over here and make a double bond. There's the correct structure. All right, for phosphorus trichloride here, we've got phosphorus, which is 5. Each chlorine is worth 7. And there are 3 of them. So I have 26 total to work with. I think 21 plus 5 is 26, yeah. Okay. We're going to put phosphorus in the middle, and I'm just going to put the chlorines around it, like that. Connect, 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 so that's 6. I'm going to put the remaining electrons on the outside. Does it matter which pair we erase to make the double bond? You can pick whichever pair you want. So if you erase the one on the top and left the side and the bottom, that's fine. So I put in all my dots. All the chlorines have an octet, but I have 2 left over because I only used 18. So those 2 are going to go here. And no double bonds are needed because everyone has an octet. So there's our solution. All right, we got SiCl4. Chlorine still has 7. So this should probably be 32, right? Yeah. So 2, 4, 6, 8 means I have 24 left. And then I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Hey, that was all of them. Look at that. And everything has an octet, so we're all set there. Excellent. Next, we have CH2O. This is actually called formaldehyde, just in case you were curious. I'm sure that formaldehyde is a chemical that most of us have heard of. It's used in preserving corpses in a moratorium or a morgue. It's also used to clean surgical equipment because it's a very good disinfectant. Each carbon is worth 4. Each hydrogen is worth 1, and there are 2 of them. And each oxygen is worth 6. So 4 plus 2 is 6 plus 6 is 12. Carbon is the central atom. I'm going to just put everything else around the outside. Then we'll connect 2, 4, 6, so that's half my electrons. I'm going to put the remaining one on the outside atoms. I don't need to do anything with the hydrogens because they're satisfied. They have their duet. But this oxygen up here could use 6 electrons to give it an octet. Now, I don't have an octet everywhere. My carbon here only has 6 electrons around it. It's only got 3 bonds. So I need to make another bond. So I'm going to take a pair off of oxygen and put it there. And that will give me the correct Lewis structure. All right. Now let's do C2F2. This is where they start getting a little more complicated. But it's nothing that we haven't done already. So each carbon is worth 4, and there's 2 of them. And each fluorine is worth 7, and there's 2 of those too. So let's see here. 8 plus 14 is 22. Now remember, if you have multiple of the central atom, try and make them as central as possible. So I'm going to put these in the middle, and I'm going to put the fluorines around them. And then I'll just connect everything. Then I'll put remaining electrons on here. 2, 4, 6, 8, 10, 12. So I have 4 left. The remaining 4 go on the innermost atom. There's 2 of them in this case, so where should I put them? I might as well give something an octet, right? But if you spread them out evenly, that doesn't matter. Because what you're going to realize is that, oh, this poor carbon right here doesn't have any extra electrons, so I need to start making additional bonds. Now, remember what we said earlier. Fluorine only wants to bond to one thing. Right? And carbon wants to bond to 4 things. So the best answer to do this would be to take this and put it here, and take this and put it here. Now, if you made double bonds with fluorine, what would end up happening is that would actually be marked incorrect because fluorine doesn't get observed to do that, which is why we have that slide that said the number of bonds things prefer to make is 8 minus the group number. So be mindful that you're not trying to double bond or triple bond with fluorine because it won't do that. Chlorine won't do that either, and neither will oxygen. Or not oxygen, I'm sorry, bromine or iodine. Oxygen will only make 2 bonds, but carbon wants to make 4. So don't leave electron pairs on carbons because that will mean it will not be making 4 bonds, and that would be incorrect. All right, I do have to... Oh, I'll just scroll over here. I have more space I could work with. So let's do C2H6 now. Same sort of idea here. Each carbon is worth 4, each hydrogen is worth 1. There are 2 carbons and 6 hydrogens, so this gives me 14. I'm going to draw my structure with the carbons in the middle. I have 6 H's, so I might as well try and spread them around evenly here. And we'll just connect everything. 2, 4, 6, 8, 10, 12, 14. Oh, look at that. Easiest molecule ever. Sometimes it just works out that way. You make the structure and you're like, oh, it's done. Cool. And then for CNBR, we've got 4 plus 5 plus 7 is 16. Carbon was first, so we'll put it in the front, and the other ones go around it, and then we'll connect them. So that's 4, so we have 12 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's all my electrons, but I need an octet around carbon. Remember, bromine is group 7. It only wants to make 1 bond. Nitrogen wants to make 3. So what's going to end up happening here is that this will share its electrons, and bromine won't. So this is the correct structure. There you go. That's your crash course on Lewis structures. And that's all we're going to do for this class. Like, in 161, you're going to study Lewis structures in much more detail. And you're going to do all sorts of Lewis structures and then explore the geometry of molecules. This is as far as we go in this course. So as long as you're able to make basic Lewis structures and understand how covalent bonding works, then you're in good shape. All right. Any questions, let me know. I believe that that's the end of the chapter. So we'll get our little celebratory hooray. All right. And then we'll go on to the lab questions. So I'll just blank this out real quick. Oh, I need a second to actually open the lab. I had it open. There we go. All right, so there were some questions on... I hit the wrong button there. There we go. There are some questions about the lab worksheet. So let's see here. 6 through 8 on the analysis of the unknowns. So let's go find that. So what you're going to do is in the video, Samita shows you all of the known chemicals, and you record your colors. Then in the video, Samita shows you 3 unknowns, and they're numbered number 1, number 3, and number 5. Unknowns number 1, 3, and 5 are something that you have seen before in the known chemicals. So you're going to assign each one based on the color. So if you saw something that was known and it was blue, and then in the unknowns you saw one that was also blue, they would be the same thing, and you would state that. So for those 3 questions, you're going to pick what you think those unknowns are out of the known compounds. And then what was the other question? Number 14 here. All right, so you know all about ionic compounds and how to make them. Now, in the experiment, let's go to this page over here real quick. Will this do what I want it to? Yeah, there we go. Okay, so in the experiment, you did a conductivity test. And when you put something into a container, so here's my container, and if the solution contains something that splits into ions, then the solution was conductive. Oh, sorry, there's a, hold on. There's a window over. There we go, that's part of my screen there. And if you put a solution in that does not split into ions, then you observe that it was non-conductive. Now, how conductive something is only depends on how many ions are formed. Okay? So, the solution that we used to make this dissociate was, the ionic solution that we used was NaCl. And we used various concentrations of it. So I think we used 1 molar, or 0.1 molar, 1.0 molar, and 4.0 molar. Now, based on how many ions sodium chloride would make, it will give you some conductivity, which is shown in the video. Now look at potassium hydroxide, which is what the question is asking about. How many ions will it make, and what's its concentration? Use your data to answer the question. Now, conductivity is not chemistry. Conductivity is just physics. So the identity of the stuff doesn't matter. So KOH should behave similarly in some way that you can discern the answer to. And that's really all I can say without just giving away the answer. All right, those are the only 2 questions that were offered, so that's all we're going to do, I guess. I'm going to turn this back on because I will forget to. That's just the PowerPoint. And we'll turn this off. And yeah, okay, so if you have any other questions, let me know. Will KOH react in the same way NaCl did? There is no reaction going on here. So I don't know how to answer that question. So we're not doing chemistry here. We're just looking at the number of ions. How many ions are present in NaCl? How many ions are present in KOH? And you can answer that by looking at Unit 9. What are the ions present when you see a K and an OH? What ions are formed? How is that similar to NaCl? Can you draw the same conclusion? That's all I can say. I can't really say anymore. I guess to answer what you wrote, so KOH won't react in the same way because there isn't a reaction, but it will behave in the same way. Hopefully that helps you. All right. That's all we have for today. Because we finished Unit 10, I'm going to put the Unit 9 and 10 quiz up online. It will be due in a week. Tomorrow we're going to start Unit 11, which is nomenclature. Nomenclature is kind of obnoxious. This is the part where the class starts to get more challenging because we're going to start throwing a lot of rules at you for stuff real rapid fire. And then after Unit 11 is the return of math. So we'll be getting our calculators back out for Unit 12 for the remainder of the quarter. But until then, look forward to just some more naming and some conceptual stuff tomorrow. See you then.